Last time, we talked about how to set up the flywheel system and how to do a simple test stand. Now we will need to go deep in the how-to, so buckle up boys, this will go deep, if needed. There is examples and links in the description. So to calculate the transfer function, we will inject a blind command into our roll system and see how the entire rocket system reacts. So for example, after 30 seconds, we put the motor at 50% of its speed and we record at the same time with the gyrometer what is happening. And this is called a step response. And it allows us to know many characteristics of our system. Its reaction speed, its stabilization time, its gain, etc. And then, with this data, using the MATLAB Simulink software, we are able to approximate the transfer function of the real system with the real data from your real rocket test stand. MATLAB Simulink is currently the standard for many things, but it's slowly being replaced by Python solution. So if you know a way to do this in Python, feel free to mention it in the comments. But for now, you know where to go. Okay, I'm only half joking. MATLAB has a trial version where you can get everything you need for free for 30 days. And there's also an online version. But it doesn't have everything we need. Anyway, go for it and try it. MATLAB is a very handy piece of software, especially if you want to do aerospace project. I've put the links in the description. So after installing MATLAB, we use and open the system identification module and use it to find a transfer function that fits well with our data curves. But before that, our curves will need correcting because, as you probably suspect, our test stands isn't perfect. There's still friction and oscillation. So I advise you to apply a friction correction in the form of friction compensating slope. Normally, a steps response curve should look roughly like this. So once you have usable input data and a record of the command you used, you can generate the transfer function. Oh, and please don't forget to record the voltage of the battery. We will need it later. So now we know what's inside the black box. It contains a function we have obtained with MATLAB, and in Simulink, you can place a function block and write this function inside it if you want to simulate it. But it's not over yet. Now you know how your systems react to an order. But we haven't done something very important yet. We haven't closed the loop. Our current system is what is called an open loop. When we send the command, the system reacts, and we can't do anything else. We don't even know the state of the system. If we want to continue to act, that is, continuously reacting to the actual state of the rocket, we must close the loop. So we take the final state, we bring it back to the beginning, and we are going to calculate the difference. So we are actually going to subtract, and what we obtain now is called the error. Don't make the same mistakes as we did, because we forgot to put the minus sign in the program here, and when you reverse that, the system goes haywire very quickly. Now what was previously the command becomes the desired state, so in our case a rotational speed. Unfortunately, after this change, we can just leave the system as is. We need to correct the error by sending the correct speed command to the motor, and for that we will use a regulator. A regulator is a type of control system where the error is used to send a correctional command, and that's why it's also called a controller. There are many of them, but the one we are interested in is the PID controller, for proportional, integral, derivative. The proportional part of the controller is very simple. We take the error, we multiply it with a constant k, and we apply it as a command for the motor. With the right k value, this will work. But the problem is that we tend to overshoot the value well before returning to it. And we eventually stabilize, but not very quickly. Okay, I will need to explain a bit. So, a little tangent. Stability is the property of a system to stabilize on a value. An unstable system will diverge with enough time. The speed of this stabilization is called the settling time, and the overshoot is, the overshoot. We want to stabilize rapidly, but we want to not overshoot a lot. And this is a trade-off. You will not have both. End of the tangent. So now we add the derivative component, which is the derivative of the error multiplied by a constant d. This component's job is to look into the future. It slows down the duration a little bit, but above all, it absorbs the overshoot and stabilizes faster. In fact, it does the same thing as you do in a car. For example, when you sense that you are reaching the desired speed, you start to stop accelerating before reaching the desired speed. Finally, we have the integral component, which is quite special, and it will come back later to make us regret using it. If your controller reaches an error of 0, it will stop working and doesn't correct anything further. So if the system is naturally stable, there's no problem, it doesn't move anymore. But in most cases, the system isn't stable and the error increases. Then the correction process resumes and tries to return to 0. But it never truly returns to 0. In fact, it's always close to where it wants to be without ever reaching it. Because when it reaches 0, it stops correcting. The role of the integral is to sum the error over time to increase the correction until the desired value is reached. Therefore, it is the sum of the errors multiplied by a constant I. To put it more clearly, it's like doing planks. If you want to stay in that position, you will have to constantly exert an effort. Just because you've reached your desired position doesn't mean you can rest. The integral component is constantly pushing to maintain the required position, even when the two other components are resting. Okay. Now our problem is that we don't have any idea of what the value of k, d and I are. And if we find something suitable for the k value, changing d or I requires changing everything. So we will need to use our simulation. In MATLAB, we will use systool and PID tuner to calculate the value of our PID controller. This will ensure stability. We can vary many parameters, like the robustness and settling time. I will let you discover how to find a good controller for your system. Afterward, MATLAB will give you the transfer function of your PID. Yes, because the PID is like everything else. It's a system, so it can be represented as a transfer function. I will advise you to stick to reasonable things and test a bit in MATLAB and Simulink before trying any real testing. Because yes, the goal is to verify that your value works in the real world, on your test stand. You can't completely trust the software. You should always test it in real life. Except that we have a problem. MATLAB gives us a continuous transfer function. But our microcontroller is not continuous. It is digital, so it has a frequency that is fixed and given to us with the RTOS. And that's why the RTOS are important. They guarantee the fixed frequency of your loop. So we will convert the continuous transfer function of our PID into a discrete transfer function using the C2B continuous to discrete MATLAB function at the frequency of the RTOS. And there, finally, you have the transfer function you want to put in the TNZ. So now we want to put it into our microcontroller. Except that we will have to do a little bit of math. Here is our PID transfer function, and here is how we integrated it. It's fairly simple to calculate, although there are some things that are complex to understand. Also, you will probably not have exactly the same shape of PID transfer function, and that's normal. The software gives you something that works for your rocket, not something out of the book. So even if the function looks different, if you follow the step I've displayed on the screen, everything should go well. Now we can finally code our regulator directly in the TNZ. And we will also be able to do our first test. So we install the rocket. We turn it on and set it in rotation. In the code, we ask it to do nothing for 30 seconds and then to stabilize to a rotation speed of 0. So in 2023, at around 11 PM in an apartment building near Paris, two idiots shouted very loudly of extreme joy in the staircase of their building. This was not the first test, nor will it be the last. But it was the test that confirmed it was possible. The rocket stopped dead. It was incredibly impressive. It was as if a god had arrived and told the rocket to stay still and not move anymore. It's absolutely incredible that we, mere students, have managed to simulate it in our own computers. Physical phenomena that we've only understood for barely 100 years. And after that, we were ready to leave for the sea space. Well, not completely. Actually, there is still loads of things that we need to do before we have a chance to launch. Well, first of all, the code I gave you isn't going to work as is. You need to add quite a few things to it. First, if you use the raw sensor data in the system identification tool, you don't need to modify the input of the controller. It is already adapted to what your sensor gave you. So that's something you don't want to modify. But before controlling your motor with PWM, you must adapt the command to the battery voltage. And so that's why you need to record the battery voltage during your first test without a controller. So I have my motor command adapted to the power of the battery now. So if my battery is a bit low, we ask more to compensate. And on the other side, if the battery is high, we ask less. Next, it must be taken into account that the motor has a maximum speed. And so when we reach the maximum, we must not ask more than the motor can possibly do. And we are stuck at the maximum value in both directions. Because yes, remember, we have a bidirectional ESC. This means that the static point is in the middle of the PWM range at approximately 1500 microseconds. Yes, we will count in microseconds, because it is simpler to represent what is really being sent to the ESC in the PWM signal. So the reverse rotation goes from 1100 to 1000 microseconds, and the forward rotation goes from 1500 to 2000 microseconds. And that's not all. Your engine can't run too slowly either. If I try to make it work between 1420 and 1580, it will stall and stop work. So if my PID asks me to send this correction command, we will command nothing. 1500, dead point. We don't try to move it. Also, in the rules, you shouldn't control the roll while the rocket engine is powering your rocket. Therefore, a timer is needed. It will allow us to activate the roll control a little bit after the end of the engine planned thrust. And I will also advise against stopping the roll control before the chutes opens, because otherwise your rocket will suddenly spin very fast on its roll axis. So what we had planned was a slow deceleration phase after the chutes opened. Finally, there's one remaining scenario, that the rocket has no roll at all. Because yes, it happens. If you're not sensitive enough, the rocket will not rotate, at least not enough to trigger the stabilization. So we have made the choice to control the roll, not to cancel it. We plan to turn on ourselves at the desired state, and in one direction. It will be a reasonable speed of 1 turn in 15 seconds, which is really slow. But this would also have allowed us to validate the experiment with the views of the cameras, which will slowly rotate on themselves. And it's still not over, because there is a big part we haven't talked about yet. But honestly, for many projects you can stop here. But we are seriously messed up, and there's still a major problem in our system. And that's also one of the most interesting. So indulge me, because we will talk about the wind-up. Do you remember when I said that the integral part of the PID will cause us problems? Imagine you have a rolling machine that starts and you activate the motor at full power, but quickly you will reach the maximum that your motor is capable of providing. However, your system did the job, in the sense that the rocket gently begins to slow down and return to speed command range that you can manage. Except that during this time, the integrated error, which is constantly being added, keeps accumulating. But since the motor is at maximum speed, there's nothing we can do but wait and accumulate even more integral correction. Then we accumulate, and when the value returns to the controllable range, the integral error is so large that the controller will simply order the motor to continue running at full speed. And the roll rate will simply cross the control range and start again on the other side, with a roll equal or greater than what we had before. That's the wind-up, and you will notice it's pretty silly. Basically, the integral just needs to calm down when we are saturated. And that's what the anti-wind-up does. We use the back calculation method, where basically we calculate the value of the error, which is overestimated, and subtract it from the error sum of the integral, with a small gain named k wind-up. To determine this gain, the best way is to add it into our Simulink, add some saturation, and try several values in multiple simulations. Except that this is true once again for a continuous PID, but we are not continuous. So once we have found the gain, we have to recalculate everything with our new formula. This time, we will have to decompose the three components of the PID and convert each one to discrete. Now we need to transform the integral component and the anti-wind-up along with it. We need to recalculate the PID entirely by hand and step by step, which gives us this function, which we can finally put in the TNZ. And after doing all of that, we perform the final test where we ordered the motor to go into saturation. And once saturated, we launch the new PID with anti-wind-up. And when the system returned to the control range, the rocket stabilized, so the test was successful. And after all of that, we were able to go to the Sea-Space campaign and launch this rocket. But as you know, or maybe you don't know yet, on this channel, we are not the luckiest. A problem with the rocket engine that were installed by the organization sent the rocket straight into the ground, and we were unable to save any SD card. And in fact, a friend of ours who had equipment for recovering data from broken SD cards had his equipment burned by our SD cards. Sorry. Fortunately, the telemetry gave us some data, 1 data point out of 4. So we were able to see that the roll was cancelled and then started again in the desired direction, very close to our commanded value, but only after the rocket stopped twirling. So now we know we can control the roll in descent. But we didn't have much time to demonstrate it. The stabilized freefall lasted for about 6 seconds. But we already talked about all of this a while ago in this video series. In any case, what is certain is that we have learned a lot. And I think in not too long of a time, I will use what I've learned to master the other axis besides roll. Well, you know the drill, it won't be as soon as you wish. Until next time, I will see you in the next video, and I invite you to subscribe and watch it and share it if you have enjoyed it. Also, now that I have a Patreon and a more sustainable posting schedule, you can find exclusive content and early access if you make any donation level, even $1 or euros. Thank you so much for your support and see you next time.